Hi guys, in this video I'm going to continue on the topic chemical reaction and energy, and this time we will be looking at three typical classic examples of calorimetric experiments. Now if you are not sure what a calorimetric experiment means, I advise you to go back to the previous video where I introduced the calorimetric experiment. So if you are okay, if you know what is going on, then we can now start with the first classic example. Now here we want to determine the enthalpy change of neutralization of the reaction between hydrochloric acid and sodium hydroxide. Now you know that for a neutralization reaction it is exothermic, that means it releases a lot of heat. So what we're trying to do is to measure the temperature rise as the two solutions are mixed, and then based on the temperature rise we are able to find out the heat change of the reaction, and by looking at the quantity of the acid and alkaline we are able to determine the enthalpy change of neutralization. Now remember that for enthalpy change we are expressing the energy per mole of reactant or per moles of product produced. In this case, neutralization, if you remember the definition is the energy released when 1 mole of water is formed. So that's why after we find out the heat change of the reaction of this particular reaction, we also need to find out how many moles of water is formed in this particular experiment. And then we want to translate the heat change into enthalpy change by having the heat change divided by the number of mole of water formed. Then at the end we can find out the enthalpy change per moles of water formed. So this is the idea. Now, but here, as we are talking about the experiment, you will also expect to see a lot of experimental consideration as well as some precaution or source of error. So here we are more focused on the experimental perspective. So why do we have to do this step? Like what is the advantage? Something like that. So let's have a look at these diagrams. So here, first of all, we have an expanded polystyrene cup, and inside it contains 1 m sodium hydroxide, 25 cm cube, 25 degrees Celsius. On the other beaker, we have 25 cm cube of hydrochloric acid and also at 25 degrees Celsius. We have a lid and a thermometer, and then we also have a large beaker containing a lot of cotton wool. So what we are doing here is we actually put the polystyrene cup here into the large beaker, and then we kind of surround it using the cotton wool. And after that, we are going to actually pour the acid into the polystyrene cup and immediately cover the cup with the lid and insert the thermometer inside. And then, so you can tell as we introduce the hydrochloric acid, the neutralization reaction starts, and obviously heat is released, and the heat released is absorbed by the mixture of hydrochloric acid and sodium hydroxide. To be more precise, it is the water of the mixture that absorbs the heat released from the reaction. So we are using the thermometer to measure the water of the mixture to find out the maximum attainable temperature. And it turns out that it reaches 30.8 degrees Celsius. Now, from this experiment, obviously we know that the reaction takes place like this, and then we first find out the heat change using Q equals to mc delta T. Remember, the mass here should be the mass of the total solution, and we assume that it is pure water, so it is 50 grams for 15 cm cube of the mixture. Why is it 50 cm cube? Because we are mixing 25 HCl with another 25 of NaOH. So 25 plus 25 is 50. And here we are using the specific heat capacity of pure water, which is 4.18. Now for the delta T, again, we will have the higher temperature minus the lower temperature, and this is what we get for the heat change. Now after that, we want to express the heat change in terms of enthalpy change. We have to look at the number of mole of the water that is formed. Um, Knowing that they are in all 1:1 ratio, and knowing that HCl and NaOH, they are all equal molar, right? Because they have the same concentration and volume. So basically, the number of mole of water formed would be equal to the number of mole of HCl or number of mole of NaOH. So we can simply choose one of them and then plug it in as the number of mole, and then we do the division, and at the end we got the standard enthalpy change, enthalpy change of neutralization. Now you see it is negative because it is an exothermic reaction. Okay, make sure the unit is kilojoule per mole. Now, regarding the regarding the experiment, of course, we have a lot of remarks. First of all, you see we use an expanded polystyrene cup. We also use the cotton wool, and for all of these use or choice of apparatus is to ensure that there are less heat loss to the surrounding. We want to reduce the heat loss to the surrounding. So all of these are to provide better heat insulation. Okay, reduce heat loss to the surrounding. Okay. Uh, the lid and cotton wool also serve the similar purpose. The lid is to prevent heat loss by convection, and also the lid may prevent the water from evaporating out from the cup, although it doesn't really that significant. After all, the reaction doesn't get really hot, but it has such a purpose. Or it also prevents dust or dirty particles from getting into the cup, right? Now here you notice that just now I said that this one and this one we are assuming that they are pure water, and we are also using the specific heat capacity of a pure water. But you can tell it is not pure water inside the cup. In fact, it is a sodium chloride solution. So sodium chloride solution will not have a density exactly equals to 1. Also, sodium chloride solution will not have a specific heat capacity exactly equals to 4.18. We are taking the assumption because we want to make things simple. But you need to bear in mind that this is also a source of error. Okay, so here the specific heat capacity of the resulting sodium chloride solution is assumed to be the same as pure water for simplicity's sake. But you can tell it is a source of error. Okay, so bear in mind all of these experimental consideration. Okay, now next page here. This part is concerning about the strength of acid and alkaline. So as you have learned in topic 4, acid and alkaline, you know that the strength of acid also affects the heat released as they undergo neutralization. Now, the reason is because we say that for strong acid, they completely ionize in water to give us H plus AQ. But for weak acid, they do not completely ionize. Instead, they just partially ionize in water to give H plus. Now, even though you know that for a neutralization reaction, no matter it's a strong acid or the weak acid, all of its ionizable hydrogen atom will be reacted with the base. So it doesn't matter the strength, they will react in the same quantity. All right? However, in order to further ionize those ionizable hydrogen atom of a weak acid, you actually need to provide it with extra heat. Okay, so that's why as the neutralization is exothermic, for weak acid, they actually use some of the heat released to allow it undergoes complete ionization so that all of its ionizable hydrogen atom can actually react with the sodium hydroxide or whatever base it is. So this is the reason why if you look at these two examples, the first one is a strong acid with a strong alkaline, and the standard enthalpy change of neutralization is 50 something. But if you use HCN, and HCN is known to be a weak acid, then you notice that the standard enthalpy change of neutralization is much less exothermic. So comparing to this, probably for HCN, it has utilized 44.2 kilojoule per mole of heat that has released it to assist its ionization or for the complete ionization of the weak acid HCN itself. So that's why it is much less exothermic. But bear this in mind. No matter it is a strong acid or a weak acid, they produce the same number of mole of water. Okay, so do not students usually have a misconception by saying that as a weak acid they partially ionize in water, so they produce less H plus AQ and therefore requiring less amount of sodium hydroxide for complete neutralization. This is a wrong concept because at the end all the ionizable hydrogen atom of HCN will be neutralized. It's a matter of whether it needs to absorb extra heat for the complete ionization. Okay, so this is the idea. Now, so if you look at this practice question, so this practice question is mainly in reference to the previous page. Again, it is a very similar experiment, but this time we are using different acid to perform a similar experiment. So I want you to spend some time working on this practice question. You can pause the video, and after you have finished it, you can resume the video and check the answers. All right, so let's have a look. So right now we have nitric acid 1 m, 50 cm cube, sodium hydroxide 1 m, 50 cm cube, so altogether will be 100. The initial temperature is 21, the final temperature is 26.1, of course, because it's exothermic. Specific heat capacity of water is given, but this time pay attention here. They also have something extra. They also tells you the specific heat capacity of the calorimeter and the mass of the calorimeter. So very often when we talk about errors, we say that the specific heat capacity of the apparatus is neglected. So that may be result in an underestimated result. But here, you see from the question, they actually provide you with the specific heat capacity of the calorimeter. So when we perform our calculation, we also have to take in account for the heat that is absorbed by the calorimeter. Okay. Now, first of all, balance the chemical equation. So this one should not be too difficult. Nitric acid reacts with sodium hydroxide to give you sodium nitrate and water. All right. Then we need to calculate the standard enthalpy change of neutralization. So you know, whenever we're doing this, we separate it into two parts. First of all, Q equals to mc delta T. Right? Now, this time you need to pay attention because now we are not simply looking at the mixture, but also we have to take in account for the calorimeter. So here, actually, the heat released is not only absorbed by the total mixture, but it is also absorbed by the calorimeter. So that's why here there are two mc delta T's. So we have, first of all, I used two different colors to show you. First of all, we have our mixture. So the mass of the water, let's say water, right? W, C, W, delta T, W, plus the mass of the calorimeter, the specific heat capacity of the calorimeter, and also the delta T of the calorimeter. So there are actually two parts, right? Now, for mass, you know their corresponding masses. So for the mixture, so the mass of the total mixture is 100 cm cube, so it's going to be 100 gram. And then here, specific capacity 4.18. Delta T would be 26.1 minus 21, which is 5.1, right? 5.1, Okay. Similarly, for here, the mass is given as 100 gram, right? 100 gram. So 100, and then we also have the specific heat capacity, so 0.70. What about delta T then? Now for the delta T, actually it should have the same delta T as the solution, right? Because the apparatus is holding the solution, they are in close contact. So the temperature of both the solution and the apparatus should be the same. Otherwise, they should have heat change or heat flow in between the two bodies. So here we're assuming that there should not be any heat float, like the temperature is constant the moment we register this data. And therefore, the delta T here should also be 5.1, right? So, and after that, you just have to tap your calculator. So actually, it is like 100 times 4.18 plus 5.1, okay, multiplied by 5.1 plus 100 times 0.7 times 5.1, then this is what we get, okay? Okay, then after we get this one, then we have to look at the delta H, okay? So here, Q over N, then we have the heat change divided by the number of mole. And the number of mole, because they are, okay, they should be a 1-to-1 mole ratio, and the quantity and volume, the concentration and volume is the same, so you can just choose one of them. We can have 1 times 50 divided by 1000. Okay, and this is what we get. Okay. All right. Now see here, if the experiment was repeated with ethanol acid of the same concentration, same volume, instead of the nitric acid, explain briefly the difference in the result. So first of all, the difference would be um, the when it comes to the results, you can talk about the final temperature. So you would say the final temperature of the solution is lower. Okay, or you can say the delta H naught N U T is lower. Okay, it doesn't matter. And as you want to explain it, you will explain that, okay, since ethanol acid is a weak acid while HNO3 is a strong acid, right? So extra heat is absorbed by ethanol acid for completely ionizing is hydrogen atom to form H plus AQ. Okay? So this is how you explain it. I think at least you need to mention that since ethanol acid is a weak acid, while HNO3 is a strong acid, at least you need to mention about this. Now, the next part may not be necessary because it would be quite difficult. Okay. All right. So let's move on to the next part. Actually, we haven't finished this experiment because there is also one very common and maybe difficult part that we need to discuss, which is here. Very often, question will be asking about the heat released in the neutralization reaction as well as the maximum temperature attained in a neutralization experiment. So here there are two separate concepts. Here one of them is the amount of heat and another one is the maximum temperature. Okay? Now for these two, there are different factors affecting the amount of heat and also the maximum temperature. Now for the amount of heat, of course we are looking at the actual number of mole of H plus and OH minus that has actually reacted. Or in other words, we're looking at the number of mole of water formed, right? Now here it concerns about limiting an excessive reagent. Because now, just now, for all of those experiments, we have equal moles of acid and alkaline. But some situation where we have excessive reagent, then we have to look into the actual number of mole of H plus and OH minus that has reacted, rather than just looking at one of them. Okay, so the first part here, the actual number of mole of H plus and OH minus reacted. The second part is, of course, the strength. If it is a weak acid or weak alkaline, less heat will be released. Okay, so the total amount of heat depends on these two factors. But what about maximum temperature? Now you may argue, hey sir, if there are more heat released, then the maximum temperature should be higher, right? But actually there are also some factors affecting the total temperature rise. So you see, the first factor, like you said, of course it depends on the amount of heat released, right? If more heat is released, more likely that it can register a higher temperature. But very often we also have to look into the total volume of the reaction mixture. All right, because you can tell, right? And let me give you an example. So if 100 joule added into a liquid of 100 cm cube, the delta T is, let's say, 10 degrees Celsius, okay? So 100 joule applied to 100 cm cube, the delta T is 10, right? So if we have more heat provided to a solution, but this time it is 400 cm cube, then the delta T may actually be smaller, right? The delta T may actually be smaller because even though you have double the quantity of heat supplied to the liquid, however, with a larger volume, the delta T may be smaller. That makes a lot of sense because you know Q equals to MC delta T, right? So just now here, yes, it is true that the Q is doubled, but you see the volume of the mixture is quadrupled. So if this one is quadrupled and the C is obviously constant, then the delta T is actually halved than the original delta T in order to make this equation stand. So that's why not only you are looking at the heat released, but you also have to look into the total volume of the mixture. Simply put, the larger the volume it is, the smaller the delta T, and therefore the lower the maximum temperature attainable in this experiment. Okay? Now, if you look at this very simple setup, acid mixed with alkaline, using a thermometer to measure the maximum temperature rise, and we perform 5 different experiments with different combinations. So you see here, 25 of each mixed together, it releases this quantity of heat and there's a maximum temperature rise. Should not be too difficult. But if you look at the second experiment, here we are using 2M, 2M. Now, having 2M, of course, the number of mole of acid and alkaline has been doubled. So the number of mole of H plus and OH minus reacted should also be doubled. So you see the total amount of heat is doubled. That makes a lot of sense. Like double the amount of water is formed. However, and also the maximum temperature rise also increased because with double the amount of heat produced but the total volume remained unchanged. So the maximum temperature rise would obviously be doubled. That makes a lot of sense. Now, if you look at here, the third experiment, you see when comparing with the first one, well, we always compare the different experiments with the first one. You notice that this time sodium hydroxide has doubled its concentration. However, you may notice that now sodium hydroxide becomes in excess. So the actual quantity of H plus and OH minus reacted is actually the same as experiment 1. Therefore, the heat released is the same. And therefore, the maximum temperature rise is also the same, knowing that both experiment 1 and 3 are of 50 cm cube in total. Now, if you look at the fourth one here, this time we try to actually compare 3 and 4 because now they have the same amount of sodium hydroxide, same quantity of sodium hydroxide, but this time we change hydrochloric acid into sulfuric acid. Now, sulfuric acid, you know, it is a dibasic acid. That means 1 mole of H2SO4 can provide 2 mole of H plus AQ. So actually here in this situation, we have double the amount of water formed when compared to the experiment 3. So that's why the heat is also doubled. And the maximum temperature rise because again, they are all in 50 cm cube in total. So the maximum temperature rise also doubled. Okay? And lastly, for experiment 5, if you compare this to the first one, now you notice they are of the same concentration, but with 50 cm cube each, actually it produced more heat, right? It has double the amount of H plus and OH minus able to react with each other. So you see the total amount of heat released, yes, it is doubled when compared to the first one. That makes a lot of sense. But if you look at the maximum temperature rise, it turns out to be the same. The reason is because as the heat released is doubled, so as the total mass of water, right? So that's why the maximum temperature rise remained the same. Okay? Now, in other words, whenever you have to think about the maximum temperature rise, you have to pay attention to the volume, the total volume of the mixture. Okay? Now, what I mentioned here is all written down here. You can read it yourself. Now, so the last part of this video, not actually, only the last part of, we can make it as the last part of the video. I'll cut it anyway. So, so before we end today's video, this is the part where we have some practice questions. And these type of questions are quite commonly seen in the exam. So better pause the video and try them out, and then we will check the answers. Okay, so let's have a look. Now, the 3 questions are very similar, but you need to pay attention to what the question is asking. The first part here, which of the following combination when mixed can give out the greatest amount of heat? So we're only looking at the heat released. So we are looking at actually the number of mole of H2O formed, right? Okay, so now the first part here, you see, you can actually do some calculation. Now here, HCl is in excess, NaOH is limited. So if you want to look at the number of mole of H2O formed, okay, this one would be 1 times 25, okay, divided by 1000, okay. For B, this time we have sulfuric acid, so here actually it becomes 2 times 25 divided by 1. The third one here, sodium hydroxide is in excess, so actually the limiting HCl will be totally consumed. So actually this is the same as the first one. And the part D here, you have 2M sulfuric acid, which is huge in excess. So actually the limiting sodium hydroxide will all be consumed. So if you're comparing these, drafts, then you can tell the one who gives the most amount of heat would be part B. Okay, that would be combination B. Now question 2 here. Which of the following combinations of solution were mixed in? This time, the question is asking greatest temperature rise. So not only are you looking at the number of mole, so not only are you looking at the number of mole of H2O, but you can also look into the total volume. Total volume, okay? So here, the first one, 1 MHCl, 2 MnAOH, so again it is 1 times 25 divided by 1000, okay? The total volume is 50, let's put it down, okay? Now for B, 50, 25, 1M, 2M. So here, you need to look at the number of moles. So this one is 1 times 50 divided by 1000. This one is 2 times 25 divided by 1000. So actually, they are of equal molar. So it is 2 times 25 divided by 1000. Okay? And the total volume is 25 plus 50. So let's put it down, 75. Okay? For part C, for combination C, so here you can tell HCl is largely in excess. So actually you can neglect it, but let's just put it down again for better comparison. So the NaOH is limiting, so they are all reacted, and the total volume is 75. Okay? And the last one, 50, 50, 2M each. Okay? So you can put it down, 2 times 50 divided by 1000, and the total volume is 100. Okay? Now, if you look into all of these combination, so some of them you can easily rule out, which is C. C is definitely not correct because, simply by looking at A and C, you can tell this one should have a lower temperature rise. Okay? Now, if you compare these two, even though the volume has been increased by 50%, but the heat released is doubled. So if you compare A to B, we can neglect A as well. Okay, and lastly, we can compare B and D. Well, you can see D here releasing double the amount of heat, but the volume is only like 1/3, like 33.3% increased. So you can easily tell that this is not correct and this released the greatest amount of heat. Of course, you can always tap the calculator to find out the exact amount of heat, then you can easily establish the comparison. But just now, I'm trying to compare one by one to see which one is larger, which one is smaller. I feel like this is an easier way to work out these multiple choice questions. Okay, so for this one, the answer should be D. All right, but the last one should also be the most challenging one. So here, again, greatest temperature rise. So here, we do the same thing. This time I kind of simplify it. Okay. Now HCl, NaOH is very standard, so it's like 1 times 25. Now I do not divide it by 1000 because I feel like you understand, you should be able to follow at this moment. Total volume is 50. Now here 2M, 2M, right? But heat is 25, 50. So the one that is limiting is the HCl. So it is like 2 times 25. But the total volume is 75. Okay? Now, see here. So the one that is limiting, actually, the one that is limiting is HCl, right? Now here, 50, 2M ammonia. Now again, first of all, no matter it's a strong base or weak base, when it comes to the number of mole of H plus and OH minus able to react, we count it at the same thing. So if you look at the number of mole, obviously HCl is limiting. So here, 1 times 25, and the total volume is 75. But pay attention, ammonia is a weak alkaline. So weak alkaline release much less heat. So actually you can already erase or cancel out this choice. But let's just put it down. And lastly, 50 cm cube 2 MHCl, 25 cm cube 1M NaOH. So here, again, the limiting reagent is the sodium hydroxide. So it is 1 times 25. The total volume is 75. Okay? Now we can compare. So just now this one we neglected because it's a weak alkaline. Then we can compare something else like A and D. Both of them release the same amount of heat, but the first one is only 50 cm3. So this one is ruled out. And lastly, we can compare A and B. So double the heat released, but only 50% increase in volume. So I think B is a better choice among all of this. So the answer should be boy. Alright, so that's it for this video. In next video, we will continue by discussing the other two classic examples.